In this lecture, I'm going to start the next CO, that is active vibration control. So the CO statement is explain the active vibration control techniques. So in this CO, we are going to discuss about the use of active control methods in the control of vibration. So we know that vibration control can be split into two halves. One is passive vibration control and another one is active vibration control. In the case of passive vibration control, we don't need to give any energy input to the system. So the system itself will operate without changing its parameters. In the case of active vibration control, we need to give a energy input and we can adjust the parameters and properties of the system so that we can achieve high effectiveness of vibration control. So we'll start with what is active vibration control. So active vibration control is the active application of force in an equal and opposite fashion to the forces imposed by the external vibration. In active vibration control, we are going to apply a force with same magnitude and in opposite direction of the externally applied force. So you can see the graph. So the first one is the incoming vibration. So it starts in the positive direction and it's a pure sinusoidal wave. So with the help of active control, I'm going to provide an actuation to the system and that is moving in the opposite direction of the applied force. So I'm going to sense the applied force with the help of a sensor and I'm going to apply an opposite force with same magnitude. So when these two forces join together, then this will be your movement of the system. Okay, so the blue line is the incoming vibration and the red is the vibration that is produced by me with the help of actuator. So when these two joins together, then the net effect will be zero. So the system will be stable. So this is the outline of active vibration control. We are going to apply an equal and opposite force to the system so that the system will not vibrate. So the applied force will be nullified with the help of the externally applied force will be nullified because of the artificially applied force. So this is an example of active vibration control. So here this is the system to be controlled. Acceleration sensor is fixed here. Okay. So the movement of the system is sensed by the sensor and it is sent to the control unit. And from the control unit, the signal is sent to an actuator. For example, if the arm turns like this, then the actuator will pull the system. Okay. So if the arm moves to the right side, then the actuator will apply a push to the system. Okay. So this will keep the actuator in the, arm in the same position. Okay. So this is how we can use the active vibration control. So first we'll start from the system requirements. Before that, another example on active vibration control on buildings. So here, the first image, you can see that this is a normal vibration control technique. Here, there is no active control strategies are used here. So when the earthquake is produced, then it will vibrate the entire building. So the second one is active vibration control is imposed here. So here you can see that the sensor is connected on the building as well as the ground. Then the signal from the sensor is sent to the computer and from the computer the control signal is sent to the actuator. Okay. So when the earthquake is produced, then the actuator will vibrate the system in the opposite manner so that the vibration will not be transmitted to the building and the building will be in a stable position. Okay. So we'll start from the system requirements of active vibration control. What are the basic requirements for a system to implement active vibration control? So the first one is a platform. Okay. So this platform is used to keep the actuator, sensor and processor, all those things. Okay. So here in this image you can see that the platform is the mass because I am going to fix the actuator and sensor and the mass. So this is actually a single degrees of freedom system. A spring is there, a mass is there, and a damper is connected here. So here I am going to fix the actuator and the sensor in the mass. That is why here the M is my platform. Then the next one is a sensor. So the sensor is connected to the mass to measure the vibration of the, in the case of accelerometer, it will measure the acceleration signal. In the case of any transducer, then it will measure the displacement of the mass. Okay. So here the sensor is used to measure the signal, and we know that in general the vibration is produced in three directions. So we can use three accelerometers to measure the vibration on all the 3 degrees of freedom, X, Y and Z. Okay. So three accelerometers should be used, or otherwise we can use a same single triaxial sensor. So the triaxial sensor will measure the acceleration in all the three directions. Okay. So instead of three accelerometers, we can also use a triaxial sensor. Then the next one is an amplifier. Okay. So the controller will calculate the desired output of the actuator. Okay, so it will process the signal given from the sensor and it will send an output to the actuator. But this output from the processor will be in low amplitude. Okay, and it will not be enough to actuate the actuator. So I am going to use an amplifier to improve the signal levels. Okay, so the purpose of amplifier is to amplify the input signal. Okay, then finally the controller. So the controller is actually the processor. In most of the cases, a PID controller will be used. Okay, so it will compare the output and input and it will give a output signal to the actuators. Okay, so that the actuator will produce a vibration in the opposite direction to control the vibration of the mass. Okay, so you can see that. So this is an active suspension system of a car. So this is the chassis and this is the engine. So the accelerometer, you can see here, it is fixed on the chassis. It will measure the vibration of the signal. You can see that. So this is the vibration produced by the vibration signals of the chassis. And it will give the input signal to ECU, electronic controller unit. And the controller will process the signal and it will send the output to the amplifier. So the amplifier will amplify the input signal and it will send the output to the actuator, and this is the signal of the actuator. Okay, so this is moving in the positive direction and it is moving in the opposite direction. When these two joins together, then you can see that you will get a zero net effect, that the chassis will not vibrate. Okay, so all the vibrations will be controlled here. So you can see the animation. Okay, so here this graph shows the amplitude of the road surface, and here the active control is used. So the green color is the sensor and it is sensing, it is giving the signal to the controller, and from the controller it is given to the amplifier, and from the amplifier, so this is the actuator, it is given to the actuator. So here you can see that. So you have to keep one thing in mind, we cannot completely reduce the vibration, but we can somehow try to minimize it. Okay, we cannot neglect it. Okay, so this is the input to vibration signal and this is the output signal. So this is the signal of the chassis. Okay, so you can see the effectiveness of active vibration control. So the control systems. So there are two types of control systems are there to process the input signal from the sensor and to give the output to the actuator. So in general, two things are used. One is a electric switch and another one is a thermostat valve. So in the case of any thermal applications, then thermostat valve is used, because in most of the heat transfer application, the thermostat valve is used. In case of vibration, we can use some electric switches or some electronic controller. Okay, so it has to compare the input and the feedback from the output, and it has to send the error signal so that the system will calculate and it will send to the output. So these two control strategies can be used. In general, in vibration, PID controller or in automobiles, ECUs are used to control the sensor input and the sensor output and the actuator input. The next one is vibroacoustic control. Okay, so this active vibration control strategy can be used for controlling the acoustics. So in space shuttles, because of acoustic source, the space shuttle will feel high amount of vibration. So in that case, we can fix a sensor and actuator on the outer part of the space shuttle, and we can reduce the produced acoustic noises, okay, because it will produce high amount of noises when it because it is running with a high Mach number, okay, it is actually running with supersonic speed. So in that case, it will produce high amount of noise. So to reduce the noise, because the noise is produced because of vibration, so to reduce the noise, the actuators and signals are connected with the outside part of the space shuttle, and it controls the noise produced by the space shuttle. So this is the vibration testing that is carried, acoustic testing that is carried out in NASA. So this vibroacoustic control strategy can be used for helicopter, then launchers, then satellites, and for military systems. Okay, wherever you need to reduce the acoustic noise, then you can use the vibroacoustic control. So this is actually the use of active vibration control for reducing the noises. So the next one is smart materials. So what is the need of, first I'll tell you what is smart material, then we will see what is the need of smart materials, then what is the use of smart materials in active vibration control. So first we'll start with what is meant by smart material. So the smart materials have one or more properties that can be significantly changed in a controlled fashion by external stimuli, such as stress, pressure, moisture, pH, electric or magnetic field. So these smart materials have one or two properties, one or more than one properties. So it changes its properties when it is subjected to, maybe in some materials change its properties when it is subjected to temperature. Some material changes its properties when it is subjected to external stress. Okay. So this is smart material. We will see some examples of smart material. Before that, we will see what is the need of smart material in active vibration control. So these smart materials will be used as actuators in active vibration control, because the actuator need to give an output that is very accurate and precise. Okay, so in that case, we can give an input to the smart material, and we can give the output to the give the output from the smart material to the system to control the vibration. So a simple example that shows the importance of smart material is a composite aeroelastic wing. Okay, so this is an aeroelastic wing. So here you can see that inside the wing layer, the smart material is used. So you can see that here a piezoelectric material is used. So we know that when the load is applied on the piezoelectric, it will produce some electric pulse. And the inverse piezoelectric effect is when electric pulse is produced, sent to the piezoelectric crystal, then it will produce the displacement. So here, to control the vibration of the arrow wing, the piezoelectric material is used. So when the aeroelastic wing starts to vibrate, then the electric pulse is given as an input to the piezoelectric crystal, and it will provide an opposite actuation. Okay, so that the vibration of the wing can be controlled. Okay, so in the previous slides I have shown the need of actuator. Okay, so here we are not going to use any additional actuator. We are going to use the smart material as an actuator, and we are going to impose the smart materials inside the arrow wing, so that we can control the vibration of the arrow wing in a precise manner. Okay, so this is the need of smart material in active vibration control. So the first example of smart material is magneto-rheological fluid. So anyway, we are going to see all the smart materials in detail in this CO, but now I will give you a glance about the properties of smart materials. So the first one is magneto-rheological fluid. Okay, so these are all fluids. When it is subjected to magnetic field, it will form a chain-like structure. You can see that when the circuit is closed, it is forming a chain-like structure, and it will control the flow. So when the circuit is off, then the stiffness of the magneto-rheological fluid will be minimum. So when the circuit is closed, when the magnetic field is applied, it is forming a chain-like structure and the fluid will behave like a solid and the stiffness will be high. So this magneto-rheological fluid can be used where you need to adjust the stiffness of the system. Then the next one is piezoelectric material. So we know very well about the piezoelectric material. It will produce a voltage when the external stress is applied. In the same case, in inverse manner, we can provide a input voltage and we can get a desired amplitude as the or displacement as the output. So here this piezoelectric material can be used as a actuator. The next one is shape memory alloys. So this shape memory alloys or shape memory polymers will remember its shape. Okay, so it will deform large in a high amount when it is subjected to temperature or stress changes, and when the temperature or stress that is externally applied is removed, then it will come back to its original shape. Okay, so it will memorize its shape and it will regain its original shape once the temperature or the external load is removed. Okay, so that is the property of shape memory alloy. Then the next one is magnetostrictive materials. So this magnetostrictive material will change its shape when it is subjected to magnetic field. You can see that when it is in the vertical direction, then the height will be maximum and the width will be minimum. When it is in the when the magnetic field is applied, it will form a chain-like structure, and when it forms a chain-like structure, then this will be a vertical line. Okay, so when this is like a vertical line, then it will be like this. So when the magnetic field is applied, then the height will be reduced and the width will be increased. Okay, so this is the property of magnetostrictive material. So here also these magnetostrictive materials can be used as a actuator, but the displacement will be very minimum and you can get a high precise output from the magnetostrictive materials. The next one is magnetic shape memory alloys. So it will change its shape when it is subjected to magnetic field. Okay, so when the external magnetic field is applied, then this will change its shape. The last one is holochromic materials. So these are all generally used for indicating the corrosion in the pipelines, because the holochromic materials will change their color when a result of change in acidity. Okay, so when the corrosion is formed on the pipelines, then this will change its color and we can identify the corrosion in the pipelines. Okay, so these are all some of the smart materials used for active vibration control as well as for other condition monitoring applications. Okay. From the next lecture, we will see the properties and uses of the smart materials in active vibration control one by one.